So what are we really doing when we approximate that curve by a straight line? So let's see. So in general terms, the equations for this circuit were Vs minus Vd by R equals f of Vd, and for the particular case of the diode, this f of Vd was Is exponential Vd by Vt minus 1. Okay. Now let me say that the first solution or the operating point that I calculate is for Vs equals Vs 0. Okay. So that means that this blue stuff here I calculated when Vs was equal to some value Vs 0, it does not matter what it is, it is basically the first thing I calculate. So this is Vs 0 and this is Vs 0 by R, and this is the operating point solution or the original solution, and let me call those values as Vd 0 and Id 0. Okay. So Vd 0 and Id 0 are the operating point of the diode. Okay. And this has to be got by nonlinear analysis. And this is of course usually numerical. Okay. And let me say that at the operating point, the diode voltage is Vd 0, I denote it like this, and the diode current is Id 0. Okay. We have taken an example earlier where if Is is 10 to the minus 15 amperes and Vs is 5.7 volts and R is 5 kilo ohms. Okay. So Vd 0 turns out to be about 0.716 volts and Id 0 is approximately 1 milliamp. Okay. So this I got from numerical analysis, and that is the operating point. Now let us say that we have a different value of Vs. Okay. And I will represent the new value of Vs as Vs 0 plus some lowercase Vs. Okay. So that means that new Vs represented as the old value plus an increment lowercase Vs. Okay, I can always do this. I mean, my original value of Vs is 5.7 volts. If Vs changes to 6.7 volts, I will say that it is 1 volt increment over 5.7 volts. Okay. I can do this for any Vs, right? And similarly, I represent every quantity in the circuit, that is the actual diode voltage, as the original diode voltage, the operating point diode voltage plus an increment in the diode voltage, and so on. Okay. So all quantities are represented as the original value, which of course is called the operating point, plus increments over the operating point. Okay. So now I can write my equations in terms of these definitions. Okay. So I had Vs minus Vd by R equals Is exponential Vd by Vt minus 1. Okay. The operating point of course satisfies this equation. So Vs 0 minus Vd 0 by R equals Is exponential Vd0 by Vt minus 1, and the new value also satisfies this, that is Vs0 plus Vs. Okay, I am writing this Vs new value as Vs0 plus an increment minus Vd0 minus Vd by R equals Is exponential Vd0 plus Vd by Vt minus 1. Okay. Now, let me write it in general terms as well, not just for the diode. So, this would be in general some function of Vd, and this will be a function of Vd0, the operating point. So, this is the general equation, and in the third case I represent the general case as the operating point plus an increment. So, I have f of Vd0 plus Vd. Okay. Now, what I do is expand this in a Taylor series about the operating point. This is the significance of the operating point. I choose some operating point which is the original case for which I calculate the nonlinear solution exactly, and about that operating point I expand the new case in a Taylor series. And what do I get? I will get the function at the operating point plus the first derivative calculated at the operating point times this increment Vd plus higher order terms. Okay. Because I am going to neglect this, I am not including them. Okay. Now, what does this mean? We have already seen this in the graphical solution. So, let us say this is the operating point Vd0. Okay. So, the very first term here f of Vd0 is nothing but this part. Okay. This is f of Vd0, and the second term means a linear dependence on Vd or increment over Vd0. So, that corresponds to this straight line, that is the sum of these two terms corresponds to this straight line, and then you can add higher order terms. The next one will be parabolic and the next one will be cubic and so on, and if you add all of that you will get the exact nonlinearity, but we will stop here and use the straight line. Okay. So, whatever I said earlier, if you have not moved too far from the operating point, you can use the straight line approximation, and the straight line is the tangent to the curve at the operating point. This is what I mean. I expand the nonlinearity in a Taylor series about the operating point and neglect all of the higher order terms, that is second order and higher than second order terms. Okay. The Taylor series expansion goes like this, right? F of Vd, which is f of Vd0 plus the increment, will be f of Vd0 plus f prime calculated at Vd0 times Vd plus the second derivative by 2 factorial times Vd square. Of course, everything is calculated at Vd0 and so on. Okay. Now, you can see that these terms, the higher order terms, reduce more rapidly with decreasing value of Vd compared to the first one. Okay. So, you can always find a sufficiently small value of lowercase Vd, the increment, where these terms are negligible. Okay. As long as you have a smooth continuous function. Okay. So, So, this approximation is always valid. The only thing is you have to restrict the range of VD over which it is valid, that is all. Okay. So, now what does it mean if I neglect these? Okay. I will be left with this f of VD 0 and the first order dependence on this lowercase VD or the incremental VD. Okay. Then what I do is I subtract the operating point from this case. That is, I simply take this equation and that equation and subtract. What do I get? Can easily verify that. We will get Vs minus Vd by R to be equal to f prime calculated at the operating point times Vd. Okay. Now, what is the significance of this? This is linear in the increment Vd. Okay. Now, there is this constant, okay, that depends on the operating point, but as far as this equation is concerned, that is just a constant. Vd is the variable and this equation is linear in Vd. Okay. So, that means that it is much easier to solve than the nonlinear equation. Okay. So, for a changed value of Vs, we had to solve the nonlinear equation all over again. Now, we do not do that. We find the approximate solution using a linear equation. Okay. Now, that is a great simplification, also because there are lots of nice techniques for handling linear equations and we can use all of those things as far as the incremental quantities are concerned. Okay. Okay. So, this is the great simplification. So, in summary, we first calculate the exact solution, that is solution from the nonlinear equation for the operating point, and that we will do numerically or graphically. Later we will see how to do it by hand. Then for any other value of the input, okay, there can be more than one input, it does not matter. You express every quantity in the circuit, both inputs and internal variables, as the original, the operating point cases plus increments. Okay. And then you find that wherever you have a nonlinearity, you can expand it in a Taylor series about the operating point and neglect higher order terms, that is second and higher order terms. Then you will be left with a linear equation relating the increments. Okay. So, now you can use everything that you know about linear circuit analysis, whatever you learned in basic electrical circuits or some equivalent course, to analyze nonlinear circuits as well in an approximate way. Okay.